Hello, this set of videos is part of a resource created by CAD/CAM Educators Hub, which is hopefully going to give you the skills to be able to run some stress and FEA simulations on Fusion, as well as gaining an understanding of how to look at those results. So on this video, I'm just going to share a quick presentation, which is going to give us a course overview as well as covering Module 1. So let's jump into the presentation then. As you can see from the cover slide, this is an introduction to FEA. So hopefully it's going to give you the skills that you need to at least get started and start moving further towards those advanced skills in this area. So these are the course objectives. So number one is obviously to gain an understanding of what it is, with number two actually being how to leverage that understanding and start to actually set up some studies on Fusion. After that, we're going to be able to try and analyze the results that we create from that, as well as finally running your own independent studies without me holding your hand along the way, just to cement your understanding that little bit further. So module one, we're going to look at the fundamentals of FEA simulation. We're going to start with some definitions and concepts. So FEA and stress simulation are quite often used interchangeably, and that's generally because FEA is one of the most common forms. And what it stands for is finite element analysis. So that's just taking apart, looking at each sort of area of that part in fine detail, and it's just trying to gain an understanding of how that part will perform based on the stresses and the loads that its environment put on it. So moving on to the concepts of FEA. So it's used to see how a part will perform both under those expected conditions with the forces that would normally be put on that object. Quite often though, because we don't live in a perfect world, there are some unexpected conditions or some unexpected forces that may be applied to the part that we've created. Again, quite often engineers will do what's known as failure testing, where they keep increasing those forces until the part actually fails. That way we can sort of see the limits of the performance of that part. Generally, it's affected by four main areas: the material properties that that part is made out of, the size, the shape, and also the actual conditions that it's working under. Now, there's a reason why I've highlighted that in orange, and that will come a bit clear in a moment. Generally, some of the reasons why we would run an FEA is to check the function of the part, whether it actually fits in as a standalone component, part of an assembly, and quite often the type of industry. Mechanical and civil engineering are two of the main areas where FEA will be used. That's because obviously the part is working under some sort of stress, whether that be making a car move or keeping a building upright. Obviously, two very important factors. Again, performance needs. Do we need to reduce some of the mass, make sure the part performs as it's expected? Performance need is another area. Do we need to try and make the part withstand that same force, but also remove some of that mass? Do we want the part to not displace and move away from its original place too much? And again, sometimes we might compare different materials and see how they perform under the stresses. This might be based on things like availability, environmental friendliness, or just the different stress properties of those materials. Quite often with using simulation software, you don't necessarily need to know what's going on in the background because it's automated. I think it helps develop our understanding just to see what magic is going on behind the curtain. Generally, this is what it's going to be doing. It's going to take the starting shape that you've created in the design workspace, and it just reads that as the initial shape that it's going to work with. Step two, it's going to create a mesh file. So it's almost like a web or net-like structure of that part made up of loads of small triangles. From that, once you actually try to solve your study, it's going to run an algorithm where it runs thousands, if not millions, of calculations at each one of those points along that mesh, just to figure out how much force is affecting those different areas of that material. Step 4, this is where it comes back to us a little bit more, but obviously the computer's still doing things to help us with this. And that is the analysis section. So once the results have been generated, what we need to be able to do is run reports and actually start to zoom in and look at the different aspects that are important to us. So now that we have a bit of an idea of what it's doing, we can start to make some comparisons between physical testing and virtual simulations. So physical testing generally costs quite a bit in order to try and get the test equipment and also a safe working environment to do it in. Again, part of this cost is the fact that you need to produce the parts that you're going to test. And there's a bit of an issue with the environment in that you're usually disposing of failure tested parts as well. However, though, there are some advantages as results can often be more accurate due to environmental conditions being taken into account. Now, as I said before, there was a bit in orange about this. So when you run a virtual simulation, quite often they won't take things like heat, humidity, things like that into effect when considering how the part will actually react to those loads and stresses that you put on it. However, though, you do have the ability to run numerous simulations using different materials, different shapes, with a very limited downtime in between each study. Quite often on the software, you can test many different materials at once, and then you can compare those results to each other quite easily. Results can be analysed with more scope because what Fusion will allow you to do is hide various bodies, zoom into certain bits, it'll allow you to place probes on your results section, and that just gives you a better overall view of how that part is coping under those stresses. So that concludes Module 1, and hopefully it's given you at least a brief understanding of what an FEA simulation is, and also when and why they're going to be used within engineering. See you in Module 2, where we're going to look at setting up one of those studies for ourselves.